So we're in the circular motion chapter, and we want to talk about objects then that are obviously traveling in circles. Remember that the force pulling them towards the center, or the sum of all of those forces, is what we would call the centripetal force. So this first example problem that I want to talk you through is called a conic pendulum problem, and it's an idea of something that is hanging like this, but it's moving in a circle horizontally. You might see these as whenever you go to an amusement park or a fair, it's the swings that you would see there, where the swings are pulled outward, and then as it stops, they fall straight back down horizontally. In this particular case, we're looking at a Halloween bat that's flying there. In the class, we'll do a lab that is the flying pig lab if we're in class. And so we have this bat, and the bat then is flying around the circle going this way, and it has this certain mass here. And the radius or the length of the cord is this 0.23 centimeters. So this is going to be 0.23 meters or 23 centimeters. And we know that once it gets going, it makes this angle that is 14 degrees to the horizontal. The angle is 14 degrees to the horizontal. So when we draw a force diagram, there are two big forces that are acting on it here. We have the force of gravity that's pulling the bat downward, but then we also have the string that's pulling the bat at this angle that is the tension of that angle. And so whenever we do that, when we're done for the AP test, this is what we would have as our complete force diagram. We could break it down, though, into a better force diagram that would help us visualize it a little bit more, where we have the force of gravity that is pulling straight downward. And then we would have this tension we would break up into a tension in the x direction and a tension in the y direction. Now, the reason that helps us is because we can look at this and say, well, don't these up and down ones cancel out? So ultimately, I can say that Ty is going to equal the force of gravity. And isn't this x component the component that's pulling the object towards the center of the circle? So that becomes our centripetal force. When we do that, we probably should look at whether the x or the y is the sine or the cosine value. So if my theta value is here, I would say the opposite of that is my x. So this x component is going to be t sine theta. And my y component then is adjacent, so it's going to be t cosine theta. So if I want to find the tension in the cord, then probably the easiest way would be to look in this up and down one and use this guy. So I'm going to have that the y component is equal to the force of gravity. My y component is t cosine theta. T cosine theta, and the way I would find gravity then would just be mass times gravity. Since I'm looking for tension, I'll divide both sides by the cosine of theta, and then I can plug numbers in. So 0.16 times 9.8, all divided by the cosine of 14. And once you punch that into your calculator, you get a total tension of 1.62 newtons. 1.62 newtons. Now, if we want to find the magnitude of the centripetal force we just set up here is really the x component. So we can say that the centripetal force is Tx, and Tx we know is T sine theta. So if we plug in our values, we can take 1.62 times the sine of 14 and say that the centripetal force then is going to be 0.3909 newtons. Now remember, centripetal just means the sum of all of the forces. So that's the sum of all the forces that are pulling it towards the center. We could also say, hey, what's the x component of the tension? And that would be the exact same thing in this case. To find the bat's linear velocity then, we're going to have to associate this dynamics of the force with some form of kinematics. So we would say the centripetal force is equal to ma, and going in a circle isn't the circular acceleration v squared over r. So once we plug in our values, we could say, well, that centripetal force is going to be 0.3909. So 0.3909 is equal to the mass, 0.16, times v squared over the radius. Now, the trick here is this length of the string up here is 0.23 meters. But we need to know what the radius is that is here. So not only do we have to take the component of the tension, but in essence, we have to take the component of that distance or that displacement also. So we would say, let's see, this is going to be Lx, which is the radius. I could say the radius over L is equal to the sine of theta. which means that the radius is going to be L sine theta. So I can take and do 0.23 times the sine of 14 and then solve all of that. So take 0.309909 divided by 0.16 times both of these and then square root it. And we end up with a velocity that is 0.369 meters per second. Lastly, we can translate that velocity into a time. What's the bat's period? How long does it take for it to go one time around? By doing v is equal to 2 pi r over t. So the 2 pi r, remember, is the circumference of the circle. The period is going to be the time one time around. So I can say the period then is 2 pi r over v by rearranging this. And then 2 pi, and the radius we just said is going to be whatever this is, the 0.23 times the sine of 14, all divided by the velocity, 0.369. And whenever you do that, you end up with 0.466 seconds. And that becomes your period for the circle. So that's a conic pendulum problem. Remember that you're looking at the forces up and down will cancel out. And then the force that is pulling it towards the center of the circle is the centripetal force. In this case, that is the tension in the x direction.